point of the field. That is advancement, means it is advancing towards the end. The moment it reached to the end point, it is advance phase is finished. Second, it is betting phase. Rate of advance depends on inflow. What is the size of the stream? Rate of advance means how fast it is covering the field water. That depends on the size of the stream. Means if it is high amount of water you are applying, it will go fast. If it is less, it will be reduced. So rate of advance depends on inflow, field slope. If it is slopy, it will be faster. Soil intake, infiltration characteristics of the soil, and surface roughness. What is surface roughness? If there is crop, it will be slow in advancing, and if it is no crop, no resistance, it will be faster. So these are the conditions for advanced phase. Next comes storage phase or wetting front. Water is stored because we are supplying further water to make D-depth supply of water in the field. So storage phase begins when advanced phase ends. At the point, if it is advanced reached, then it begins the storage of water at that particular point. It occurs only if inflow to the field continues after water has advanced, means further water is coming, then only it is storage phase. And it goes until the downstream end of the field. And storage field ends when inflow ends. We control this or stop this supply, storage ends at that particular point. So storage again ends at that particular point. It depletes then, and recession phase starts then after. So depletion phase begins when storage phase ends, means there is no further supply of water, there is no further storage coming. But now whatever it is reducing. Reason being, it is infiltrating continuously. So begins this depletion phase when storage phase ends or when inflow ends to supply of water. And depletion phase ends when the depth of flow at the inflow end of the field becomes zero. Means at that particular point we have stopped inflow. There is no further supply of water, and whatever water it is, either it is moving downward because of slope or soil condition, or it has infiltrated, so it finished here. So this depletion phase ends when depth of flow at the inflow end here of the field becomes zero. There is no water on the surface. It is all water is stored in the soil by infiltration process. Now it is a recession phase, that is very much important in designing irrigation method. So recession phase begins when the depletion phase ends, means there is no water that is moving, and continues until either the front reaches the end of the field like advance, or the rate of recession, or this rate of recession depends upon the inflow rate. What is the means how much time it will go? It depends on the inflow rate, that is basically discharge condition from the supply point. The slope of the field, that is also important. Reason being, in advance it is important, so in recession phase as well, because if it is more slope, it will finish fast. So slope of the field, the infiltration capacity of the soil, how fast it is infiltrating, so depleting water is immediately reduced or finished. And the hydraulic roughness, or say simply roughness of the soil. So these are the characteristics behind designing of irrigation method, especially we are talking about surface irrigation method. So here it is next term, infiltration opportunity time, time interval during which water is available to enter in the soil between the time it arrives at the point during the advance phase and departs during the recession phase. So it is basically difference between advance and depletion time in the field. So this is the time which is called the opportunity time between advance phase and depletion phase. Vertical distance, the same, it is written here. Vertical distance between advance and recession curve, it is infiltration opportunity time. For irrigation uniformity, remember our target is everywhere in the field it should be equal amount of water that infiltrates, so that root zone depth is getting equal amount of water everywhere in terms of depth. It does not matter that it is supply point, so here it goes up to this, and it is end point, there is less water, so it is less than required condition, depth of water. So irrigation uniformity to be high, or for irrigation uniformity to be high, opportunity time must be same throughout the field. Opportunity time means this difference of what? Advance and depletion phase must be equal everywhere in the field. So that is, opportunity time must be same throughout the field at every point. That is our target, to get the maximum uniformity or possible best uniformity. When it is possible, it is normally, this is normally facilitated by flat advance curve. Advance curve means it is advancing from here to here. So if it is very fast and it is a straight line, then only it can be the highest possible uniformity condition. So for maximum uniformity, once it is curve and difference will be the equal everywhere. So how it is possible? That is our target of designing. Means let us have very high volume of water that is applied at very fast velocity, so that it is covering very fast. Means there is no time. Means immediately splash and then cut it so that it is immediately reduced. But that is not good for irrigation purpose. Reason being, one important aspect is reduce erosion. Loss of soil should not be there. Erosion should not be there. So higher uniformity can be expected on fields with steep slope. Once slope is very high, immediately water will go to this point. So minimum time it will take to advance water from the inflow point to the end point of the field. So high uniformity can be expected on fields with steep slope, low hydraulic roughness condition. There is no roughness to retard the flow of water. Low infiltration capacity, there is no loss of water, so that every water it is going directly to the bottom of the field. And when large stream size are used, means it is heavy discharge which is diverted to the field. But these are not the practical possible conditions, remember. So this is the simple idea how we can design the irrigation system or irrigation method. If you have any query related to this infiltration, advance, recession, storage, cutback, any point? Anybody? I need your answer, whether you are connected or not.
No, sir.
Can you
No.
hear me? No query. You are. So now, if you recall surface method of irrigation, there are four names or four methods. Uncontrolled, second is border, basin, and furrow. So this is uncontrolled or free flooding method. What it is here, this is just one picture. Water is flooded everywhere in the field and it is uncontrolled, means water to the field. So crop are irrigated without regard to efficiency or uniformity. Reason being, everywhere we need to flood this field. Spade irrigation is prevalent. Usually it is supply and uncontrolled, means there is no regulation. Prevalent means water is given freely. And the purpose of application of flood flows in the field is to recharge the crop root zones while moisture or maybe water requirement to grow the crop. Just like one example is rice crop. If there is huge amount of water, excess water, like usually in India, rice is grown during the monsoon season. And there is excess water everywhere. Canals are supplying. So it is just cut the field so that supply is uncontrolled in the field and it is flooding everywhere. So higher water wastage and that may result in soil erosion. So it is a usual problem. Loss of soil because of high flow of water in flooding method of irrigation. The reason being we need to divert this excess amount of water in the crop which can sustain under this flooding condition. So rice is the only crop. So this is called uncontrolled or free flooding method of irrigation, which is only and only for. At the same time, if there is a limited amount of water and even rice crop, we are though supplying water, but there is control. Like in Bengal, here, there are three crops of rice. Monsoon season, that is called Kharif, then next season, Rabi, and then Boro, that is summer season. Summer means there is no excess water, so we are supplying water to irrigate the rice crop even. It is flooding, but it is a controlled flooding. It is not uncontrolled flooding. We know that how much amount of water we need to supply for a certain period of time. Then again, once water is depleted or reduced in the field, we are supplying. So that is controlled condition. So this is uncontrolled or free flooding of water in the field. Next is, if you recall, border irrigation method. So what is border irrigation method? This is the field. We have a channel which is supplying, and suppose this is the field. It is divided into strips, or these strips are called borders. So make use of parallel earth ridges. We are dividing this whole area, suppose it's a bigger area, 100 meter, into number of strips, right? So make use of parallel earth ridges, called basically borders, to guide the seat of water that is flowing water along the slope in the field. Standard or say general condition, we can say the area between two borders or two ridges is called the border strip. And what is the width of these borders? Border strips, it varies from 3 to 30. Again, it's a matter of which soil we are talking. If it is a black soil, it is slow infiltration, then we can go for a bigger width of strip, 30 meter. But if it is say sand dominating or silt dominating soil, then we need to have a smaller width of strip so that there is least loss of water with respect to supply amount of water from the channel. What could be the length? It again depends. These are general observed condition. It varies from somewhere 100 meter near about to a maximum near about 800 meter. And strips have no cross slope, means these are labeled condition. There is no slope in this condition, cross slope. So strips have no cross slope but has a uniform slope in direction of irrigation. In this direction, it has a uniform slope. So certainly we need to prepare the land in such a way that if there is any cross slope, we need to remove that and develop a uniform slope in the direction of irrigation or towards the end of the field where we may have a drainage to remove any excess water it is applied in the field. So this is border irrigation method. In each strip, in border irrigation method, water from upper end can flow down the slope nearly uniform depth. We are simply thinking that it's a nearly uniform depth of water everywhere so that opportunity time is the same. Now put the infiltration idea. Opportunity time advanced from here up to here, and then it is opportunity time in between advance and recession condition. So simple idea is water from upper end can flow down the slope with a nearly uniform depth. An irrigation stream must be large enough to spread over the entire width without overlapping. Means simply it is going very fast, cover every part of the stream. If turned off, that is back some minutes before the advancing waterfront reaching the lower end. Means there is one way. If we need more water or a little bit more water to cover the depth d amount, otherwise here only we can stop the supply of water so that whatever water it has stored here, it can cover the last part of this strip or bottom. So stream is turned off some minutes before advancing waterfront reaching the lower end. Reason being to save the water. And water temporarily stored in the border strips moves down to it and infiltrates here at the last. That is completing irrigation coverage or completing this irrigation to this field. So that is simple method of border irrigation. This is basically adapted to most soil where depth and topography permits, means soil must be having sufficient depth. Why it is means we are discussing here? Because maybe there is hard pan or maybe rocks which are not permitting to go water down. So it is only filling to this particular point. So this is adapted in most of the soil where depth and topography is not undulating, but it has a very gentle or minimal slope towards the down end of the field. So topography that permits the required land leveling at a reasonable cost. It is not like it's dunes and you are removing everything to make a border irrigation facility in that area. But if it is within a reasonable cost, we can develop this field without permanent reduction in soil productivity. We can go for this. This is moderately low to moderately high infiltration rate soil are more suitable for border irrigation. Moderately low, that is clay type of soil, and moderately high infiltration, that is basically sandy soil. So it is suitable for those type of soils. It is not used in coarse sand, not pure sand soils, because it's a very high infiltration. No matter whatever, suppose it's a sand, no matter what is your discharge you are applying, immediately certain meter it will infiltrate all the water. So it's not used very high infiltration rate because of very high infiltration rate and very low infiltration rate soil. Suppose it's a pure clay, it will take much longer time to get infiltrated water into the soil. So it is not suitable for two extreme conditions, but in between suitable. We adopt or we can use irrigation. It is suitable. This is soil condition. Now, what about the crop? Water irrigation is suitable to all close growing crops like wheat, barley, fodder crops, and legumes. However, it is not suitable for rice. Means it is flooding that is required. So, if you can flood, you can go. Otherwise, there is no need of designing a border irrigation. But rice is grown there by flooding these borders. It is why borders? Because we have bunds in rice fields. It is called bunds. So these are at least 30 centimeter high. But border means once we are preparing the land, we are putting a small ridge there. It is not bund, it is a ridge, which is removed after the crop or which is immediately removed by any plowing implement we are using in the field. But in rice crop, these are the bunds. 30 centimeter permanent height, so that we are flooding water to store there a kind of flood condition at least 5 to 10 centimeter. So avoid any overtoppling. It is near about 30 centimeter high bunds we are placing. So there is a difference between bunds and borders, and that's why it is not suitable for rice. But if you are making a bund rather than border, it is very much flooding the area and we can use. What are the advantages of water irrigation? Water ridges can be constructed economically, means once we are preparing the land plowing, we can construct economically. Farm it is like bullock drawn A-frame. A-frame means it is like this, it is drawn by the bullock in this way, and automatically it is taking soil and making a kind of a small ridge there. A-frame ridger or bund farmer or tractor drawn disc ridger, where we have two discs and simply putting water in the form of a small ridge. Labor requirement in irrigation is reduced as compared to conventional check basin, that is the next method. Uniform distribution and high water application efficiencies are possible if we are designing there is water advancing time is reasonably less and opportunity time is uniform everywhere in the field. Large irrigation streams can be efficiently used to supply water, reason being we need to cover as minimum time the whole field as possible. And operation of the system is simple and easy, so that is advantage of this method. And its adequate surface drainage is provided if outlets are available at the bottom of the field, so that any excess amount of water which is creating problem to the crop can be drained out. So these are the advantages of border irrigation method. So how it looks like in the field here in these figures, simply I want to just show you to have some idea, like this is supply channel and these are the fields border with borders. This is the border simply, but this is the bund at the upper side or at the supply side. So there are one or maybe two inflow condition in the field, so that it is covered everywhere in the field uniformly and in time. So there are different types of borders: straight and contour. Here contour. How? Why contour? Because it's a cross slope there. So the area which is coming in the same level, it is covered by this ridge or this border basically. You can see it is not a straight line, but here it is a straight line. Here we have transformed this whole land in equal level. But here level we cannot because of economy, because of certain limitation. So we can have a kind of ridge which are not parallel but covering a certain area which is at the same level. That is usual in rice cultivation kind of condition within the field. Or in wheat, let us take example of wheat as well. When we are supplying water to cover the wheat or irrigate the wheat crop, it is usual. It is the time is straight. Or some places where it is not, it has a cross slope, we can apply water in contour ridges. Within the ridges are contour borders. So borders may be laid along the general slope of the field, that is like this slope condition, that is straight or down the slope of the field, or it may be across the slope of the field. Suppose it's a as well. That is basically contour condition, contour borders. One field can be labeled to desired slope economically. Graded borders are easier to construct. These are the graded borders, typical graded borders, that is A. Typical borders for irrigation, if it is economical to label the land. However, when slope exceeds the safe limit, means we cannot have more than, say, for clay 0.5% or 0.05%. If it is suppose 1%, we cannot have in this clay. So when slope exceeds the safe limit, fields are undulating and leveling is not feasible. Contour here means whenever are the areas which are at the same level, we should cover in the under the same contour condition. That is means contour bands. We can form the contour bands to cover the area at the same level. So we can use the contour borders for the irrigating field. Now, what are specification designing? Important based on the size and 30 meter we can have. Depends on the soil leveling condition. It can vary, or even it can go to 30 meter as well if it is, say, more clay is there. Length what 100 to 800 meter, but that is maximum condition. The soil, slope of the land, and size of the irrigation stream. It is supply rate. For moderate slope, this is one condition it is given. For moderate slope and small to moderate size irrigation stream, like maximum 50-60 liters per second, suggested as for sandy and sandy loam soil not more than 60 to 120 meters. Medium loam may go up to 100 meters, so 100 to 180 meter. For clay loam, because clay is dominating here, infiltration rate will be less. If slope is moderate, clay soils or clay loam and clay soils, we can go up to 300 meter. But suppose it's more clay condition, you can go up to maximum like this. Otherwise, what is the loss? To cover longer area, it is more loss due to evaporation as well, because it's for longer time water is here until it reaches to longest depth. More seepage are possible and so on. So losses will be more than the benefit of water as irrigation in terms of efficiency. So these are general idea we need to take into account to decide what should be the size width of the border, what should be the length of the border, and recommended safe limit of slope, border slope of usually for sandy loam. It varies from 0.25 and is there and there. So we can have greater. It's a medium loam, sand is reduced to loam, slope may be lesser, 0.2 to 0.4% in field condition. And if it is clay to clay loam condition, 0.05 to maximum 0.2% slope of the field we should take. Otherwise, it will be fast moving of water. There will be less opportunity. So in this way, we are deciding what should be the size of the border. Now, typical values for stream size, this is the simple. You can get in literature or for standard condition for a particular soil, slope condition, infiltration rate characteristics of the soil to decide what size of a stream it should be to cover maximum area in shortest time, that is improving the uniformity of the system or irrigation system. So simple example like we have sandy soil, loamy soil, sand loam, and finally it is reaching to the clay, which has least infiltration. Our infiltration rate is least with comparison to sandy that has high infiltration rate. border slope that is permitted somewhere in between this zero point 0.2 to zero point 0.4, and when this is the range of border slope, it is least, reason being infiltration is less, so opportunity time should be more here. The stream water is diverted for a longer period of time in the field, so that it is more opportunity time to infiltrate the water in clay soil. But if it is a sandy soil, infiltration rate is high, slope must be high, reason being otherwise it will be more infiltration and uniformity will be missing. And it should be a high discharge characteristic stream that should be introduced in the field, so that in minimum time it is covering this whole field. Now, design of water irrigation system, what we need to determine are determining width of the border, length of the border, stream size, slope, and duration for how long it should be, stream should be diverted, that is T, to cover the depth D, or to supply depth D amount of water in the field. So width of border, it should be such that there is no cross slope. There should not be any cross slope, but it is one directional downward slope. Within the width of the stream size should be flow with non-erosive velocity. If you recall, for channels we have taken not more than 1 or 1.2 or maximum 1.5, but still it is field, so it should be further less velocity of water, so that it is not erosive condition which is removing the top fertile or productive soil from the field. Length of the border, you have learned, it should be such that uniform intake opportunity is obtained all along the border, means everywhere in the field. In small fields, field size may govern the length, but in longer, we need to design everything. Discharge that is applied, slope that is important, and then to cover the border length. Stream size, it should be non-erosive and should give desired advance rate, means how fast water should move in the field, that is important there in designing the stream size. Slope of the border conforms to land slope and as such cannot be changed. Simple condition, once we have decided that this is the slope of the field, as a leveling we have done to design the slope of the field, we cannot change immediately or cannot be usually changed because it's not economical condition. Labor, machinery are required to make a slope condition in the field. So it is fixed when land grading operations are carried out. And we are once decided slope of the border, it will be same for quite longer period of time. So we need to design all these conditions and plan accordingly to find out high uniformity of water supply or irrigation. So here it's a optimum grade and maximum length of border for various soils. Once again, it's a clay. I have learned that slope should not be more than say 0.05 to somewhere point maximum 1. But here it is again reduced and sand soil has the maximum grade or slope. Lengthwise, it should be minimum. Grade should be more, length should be minimum. Clay should have less grade and maximum length. Reason being, it's opportunity time we are looking, which is uniform everywhere. And that's why we are adjusting these two, slope and length, so that for a given discharge stream condition, it is supplying water which is uniform everywhere in the field. Duration of irrigation, it depends on the depth of water to be applied D, and we know the discharge Q. So it's a duration. Qt is equal to simply later on it will come D into A. So you can find out this, you know that what is the discharge rate that to in the field up to root zone depth. Time we should divert this stream to the field to get proper irrigation efficiency under border irrigation. As depth of water changes with different irrigation, suppose it's the first irrigation, second irrigation in the same field, so depth changes with different irrigation. The design border, what borders we are, these are not the bunds, but these are borders. So design of border should be considered all possible depth to be applied. It should not be like at particular moment you need to apply, suppose for an example, 10 centimeter depth of water, but borders are too small to overtopple the water. So you need to take care about any possible maximum depth of water that is required to apply in the field, which can be easily controlled by these borders. Now, any query, students? I think nobody is there. Utkarsh? Utkarsh? Mr. Utkarsh? ये देखो भाई उत्कर्ष का तुम लोग फील्ड फोटो देख रहे हो कि नहीं? Anybody there? Out of 37 students, anybody there?
Yes, sir.
Yes, sir.
उत्कर्ष तो
Yes,
लाइव
sir.
है, देख लो भाई. नहीं? ये देखो उत्कर्ष चले गए. देखा? तो बोलते जाओ. Did you see? Ritik? क्या हुआ? You want to show that you are still there? Naveen? That is the beauty of online teaching. Okay, let us have a break for a few minutes and then we will discuss about another method of irrigation. Is it okay?
Yes, sir.
Okay.
Yes.
So have a break for 5 minutes and we will discuss then after. सबसे बोलो जरा मुंह धुल लें चाय वाय पी लें so that they are attentive. Okay. Okay. Let us have a break 5 minutes. Meet at 9:12. 9:06 is. Yeah. Yes, are you there? Are you back?
Yes,
Yes,
sir.
sir. Yes, sir.
Very good. At least now I hear words from you. Okay, so you have any query related to border irrigation? No query?
No, sir.
Okay, very good. That is required. Now it is second unflooded condition, uncontrolled flooded irrigation in surface, border, then basin, and finally it is fourth one is furrow. So second is basin method of irrigation. It's the simple idea here. There are two names. Check basin. Check means we are making square or rectangular shape of the field, or we are dividing the whole field in squares or rectangles, so that from the supply line we can apply water in these small checks to find out more efficient condition of irrigation. Sometimes if it is orchard and gardens, we are supplying water in a circular area, that is called the ring. So it is a ring basin or it is a check basin. You can see in the field we have ring basin, water is supplied in circular area, that is ring basin. And if it is a field like controlled condition, it is not uncontrolled now, rice irrigation itself, rice, wheat and other crops, closed space means spacing crops, it is basin irrigation. So border is a long strip. Basin, same border is divided in number of means square or rectangular parts, fields. Why? To get more efficiency. Earlier it was lesser efficiency. It was a very long, maybe 100 meters and more, up to 800 meters. But basins are smaller. And in this way, it improves the efficiency of water application. So basin irrigation is the simplest and most common method of irrigation in India. Basins, small basins we are developing in the whole field, so that better irrigation we can provide to the crop. Field is divided into small units surrounded by small bunds or ridges. Again, it's basically ridge, it's not bund, bund is higher in size. These are temporary, it's not permanent, just for one crop. After the sowing, we are developing these conditions so that water can be applied suitably to the field. Gated outlet, just like here. We can have something gated outlet if it is a pipe flow system, or it is a siphoning, or it is just opening small and then closing it. Just like here, it is opening, simple opening. We can supply water. So gated outlet, siphon tubes and hydrants conduct water from delivery channel or pipeline into the basins. Basins may be either labeled or again graded, depends on what is the topographic condition of the area. It could be a labeled condition. If it is a label, then we can make a label, or if it is, means suppose it's a slope here somewhere, so we can make a graded basin here. So in rolling topography, the ridges follow the contours connected by cross ridges at intervals. And irrigation, say simply orchards, when plants are widely spaced, just like 10 meter or more, this space is in between plants. Ring method, what you have seen, it's a ring method of basin, or ring method or circular basin are used, or basin is it is used there. So check basin types, if we want to understand, it's a label basin or it may be a contour basin. Contour means it is rolling topography, so we can have a contour basin kind of condition there. So label basin, water is introduced as rapidly as possible and then held until it infiltrates or is drained away from this area. High application efficiency is possible as runoff losses are minimized. In border, it is from the bottom of the field, its possibility of drainage or runoff generation. But here, it is minimum possibility, or there is no loss of water as runoff. Contour basin, it is constructed with two levels or levees parallel and two perpendicular to the field contours. Means it is parallel or it is perpendicular, we can have the condition. Water enters graded basins along the upper contour, whatever it is upper condition, and then it goes to lower condition and follows the lower contour until irrigation is completed in this whole basin. So we can have two kind of condition. First it is applied here and then it is going here. That is in contour basin because of rolling topography of the area. Its adaptability, where it is adapted in land condition, it is a smooth, gentle and uniform land slope. We can adopt basins. What type of soil we can have? Moderate to low infiltration capacity. The same previously we learned in border irrigation. Border irrigation, yes. What kind of crops we can have? We can have cotton, grains like paddy, maize. We can have orchard once we are putting ring basins here, or it may be a pasture. Not for the crops, this is important, it is not for the crops which are sensitive to wet soil condition. Any soil which is sensitive to wet soil condition for more than one day, it is not suitable. Size of the check basin may vary from just 1 square meter, just like vegetables we can have there, to 1 to 2 hectare basins or even more, and that could be just for a rice, since it is burned everywhere and we are simply applying water. So it is as well the basin. What are the advantages? Many crops in same field without making major change in design. Reason being, we have already labeled the field, developed the grade, so it is not required to change for different crops. It is useful when leaching is required to remove the salts because it's small area. So we are supplying water just fill here, and leaching is possible from this field itself because of salt accumulation in the soil. So useful when leaching is required to remove the salt from the soil. Conservation of rainfall, just like a rain basin in the field. Any water that is generated as runoff in this tree around, it is conserved here. So conservation of rainfall and reduction of soil erosion, that is usual in runoff process. High water application efficiency with respect to previous condition, that is border. Water covers the basin rapidly to ensure good uniformity. Reason being, it's a small area. So immediately water is applied, it covers this whole field very fast and short in time. At the border, it is longer and it takes longer time to cover this whole field. So uniformity is usually or relatively less with respect to basin. What are disadvantages? Advantages. If we have advantages, there are certain losses as well, just like ridges interfere with movement of farm implements because we have make ridges here, so they are making problem to small farm implements or they are getting broken. So that is again a question of efficiency of irrigation and loss of time as well when machine of area available for cultivation. Because of these ridges, certain amount of area is lost for cultivation. Precise land grading and shaping is required because we are developing a small piece of land which has the same label. So it is means money is involved, labor is involved. So precise land grading and shaping is required there. Labor requirement in land preparation is comparatively more with respect to and crops sensitive to the wet condition. Any crop which is not means requiring water or wet condition more than 1 day, it is not suitable method for irrigating those crops. Now, design of check basin. We need to determining size of the plot suitable for particular stream size. What size of plot or basin it should be, that is important. Duration of irrigation in order to replenish the root zone soil moisture, how much time it should be for a stream Q condition so that moisture is improved to the level of field capacity. So the amount of water theoretically required to irrigate a particular size of check basin can be obtained. The same idea I have already given. Q, we know discharge characteristics of the stream. T is the time we need to find out. We know the area. We know the required depth from the field capacity and current or present moisture content. So we can find out what time this stream should be diverted in the field. So quantity of water calculated will irrigate entire check if the opportunity time is same all over. So important idea is immediately it should cover this whole area by the stream so that opportunity time is same for every point in this field. At tail end, at the last, suppose the stream is diverted from here, so this will be the farthest point. At tail end, the opportunity time available is less because of the time required for the water to spread all over. Means it is some time that is required to spread water all over. So here opportunity time will certainly reduce a little bit. Thus, additional opportunity time should be allowed at the end of the field. Means there must be some more time so that this particular point where water has reached at the last should get almost the same amount of time as opportunity time, right? This is the simple idea of designing border and basin irrigation. So can you check this question if you can handle this? An irrigation stream of 27 liters per second is diverted to check basin of size 12 meter by 10 meter. That is the size. The field capacity of soil is 14%. The average soil moisture content in the crop root zone prior to applying water, that is basically present soil moisture content, is 6.5%. How long should the irrigation stream be applied to the basin to replenish the root zone moisture to its field capacity condition? So how long time? Assuming no loss due to deep percolation, we are simply assuming that there is no loss of deep percolation beyond the root zone depth. Means whatever water it is applied, it is used for irrigation only. The average depth of crop root zone depth D is equal to 1.2 meters, sorry, Z. And the apparent specific gravity of the root zone soil or soil within the root zone is 1.5. Can you find out the time? Anybody? I couldn't hear from you. Anybody? Nobody is there or nobody wants to talk? Ankit? Ankit Sharma? I think nobody is there.
Yes, sir. Yes.
Sir, yes, sir, we are there.
You are there? Can you do this? Find out the time. Ankit?
Yes, sir.
I know now you. Can you do this? This problem?
I'll try, sir.
Okay, you try and give me the answer. Have everybody written this problem? Did you note down the problem? That is pathetic. Okay. So I am giving you the answer. It is better to give you answer. Okay, here it's a net irrigation requirement. You can find out as the difference between field capacity and available moisture content prior to the irrigation. Field capacity it is given 14% and difference is 7.5%. You can find out what could be the depth of water to now apply to go back to field capacity, that is 14%. So you know that it's a percentage. So you can do simply 7.5 divided by 100 into a specific gravity into Z, that is the depth of water requirement. Isn't that? So this is the same condition here. 1.5 is apparent specific gravity, 1.2 is the root zone depth, and this is simply covered in different manner. And 5 centimeters in this field at the level of field capacity. What could be the total volume of water now? That is area into depth of water. So strip size is 12 meter by 10 meter. It is in centimeters, so 13.5 divided by 100, that gives you in cubic meter, because it's meter, meter, meter now. So 16 water is required in this basin. That is that is exactly 16,200 liters. And now you know Q into P is equal to, that is A into area into, what is that? Depth of water. So T is equal to, now you can find out 27 liters per second it is supplying. So how much time it will be? It requires 16,1200 liters, 27 liters per second. So 600 seconds it will be supplying water to this required amount. And that is simply 10 minutes. So divert this stream in this basin for 10 minutes to improve the soil moisture from current soil moisture to the field moisture condition level. Now, the third method, is it clear? Anybody, if you have any query, because it's very simple. Any query?
Clear, sir.
Very clear.
Excuse me,
Now
sir.
it is, yes.
Sir, when we apply it in practical situation, then what percent of error will we add to this?
That we need to find out. That is again a question later on. We need to check whether everywhere this is the amount of water, soil moisture it has reached. Soil moisture, field capacity. We need to have a few samples there. Suppose in this field we have taken 5 samples to find out the average soil moisture content. It is not average. That's why if you recall, I gave you different efficiency, field application efficiency.
Yes.
So we need to take into account, because this much amount of water will not cover. There may be deep percolation as well. So within the root zone depth, we need to take a few samples to find out whether everywhere it's the same amount of water. Otherwise, if there is efficiency, efficiency is usually not. This particular example is not a practical one. It is simply showing 100% uniformity and 100% efficiency of the system. So we need to take care into account the efficiency as well. We are talking this design in terms of uniformity. Everywhere it is same amount of water that has been applied. And efficiency, there is no loss of water, but there is loss and there is problem of uniformity. That's why we are designing the system. Did you get my point?
Yes, sir. Yes.
Okay. Okay. And now it is for irrigation. When crop is or soil is different, we cannot cover by using border or basin irrigation method. Flood irrigation, it is not required. we are using furrow system of irrigation. So you can see these are the furrows, means small channels, and in between channels we have crop in rows. So irrigation is accomplished by running water in small channels. Those are called furrows. This is supply channel, and here it's a close spacing crop. We have small furrows or small channels where we are supplying water through these siphoning arrangement. Generally, open field ditches or gated pipes are at the head of the field here to supply water in the furrows. Siphon tubes are spirals divert water into the furrow, means simple tubes or any channel that is supplying water to the furrow. Here it's a channel, or another side it's channel, and it's a long again. So water infilters in this channel, suppose water infilters at the bottom, and suppose it is flowing up to this, it is from all parts here. So you can recall the channel geometry. We have learned most economical channel section of flow. In the same way, water infilters from the surface area which is in contact or covered by the water. So water infiltrates from the bottom and sides of the furrows, moving laterally and downward to bed the soil. Means once water is moved in this direction, so either it's vertical, root zone depth is somewhere here, or crop is somewhere here, so it is laterally, like here. You can see it is wetting front, so water will move in this direction as well as in this direction to cover this root zone depth, to wet the soil and to move soluble salts, fertilizers and herbicides that is carried out with the water. So we are supplying water as well as any fertilizer through these channels called furrow. There is again, means if you recall infiltration curve, it is cut back, means stream is reduced in size or stopped as well. So cut back stream it is diverting, and to cover, means you recall that we are supplying water from here and channel is so long, our field is so long, that after this particular point we are removing supply of water, and whatever water it has stored in this portion of the channel will cover this remain area. So it is called the cut back. So it could be either stopping the supply or reducing in size in terms of amount. Initially, suppose it was applying at Q rate, now it is reduced to Q dash, that is less than Q initial condition. That is called the cutback of the stream or cutback stream. So common method to obtain the optimum opportunity time to apply the irrigation. Reason being, this is the wetted area, so it has faster movement of water, but this is non-watered area. It will allow water to move slowly with respect to this. So once water has covered a certain distance in this furrow, we can cut back is or reduced in size, so that there is minimum loss of water in this area, and it can cover this downstream remain field or remain means furrow area, furrow length in a shorter period of time. So it's a common method to obtain the optimum opportunity time to apply irrigation everywhere with uniformity. So initial design stream is allowed to flow along the full furrow length, and then stream size is reduced. So it is sometimes like cut here, or you can go until the last and then reduce the size so that water is filled in this furrow for some time. That is as well required. So resulting stream is in that way reduced size stream is called the cutback stream. Size of cutback stream is adjusted to match the cumulative infiltration in the furrow to avoid runoff at the tail. So we are cutting back or reducing the size of the stream to avoid any loss of water as runoff and allowing maximum water to get infiltered from this furrow or this furrow channel section. It continued till the time required to fill the crop root zone to the field capacity of the soil. So cutback stream after main stream size or quantity of water, it is until we have desired depth of water applied in the channel. Now, types of furrow irrigation system based on basically alignment. Straight furrow it could be, so level or graded, it could be same level or it has a gentle slope. Land slope does not exceed in this way 0.75%, 0.5 for intense rainfall regions, so that it is controlling maximum amount of rainwater and utilized as irrigation. Straight furrow and then contour furrow, basically alignment. Reason being soil or area topography is not supporting and it's not economical to remove this excess and fill here. So sometimes we are designing contours rather than having straight, we can have in this way as well. That is because of contour or slope of the area. So contour furrows overcome the sloping land limitation of straight furrows. That is usual, you know it now. Carry water across a sloping field, that is as well possible because area is slopy. Field supply channels run down the slope like here. Light soils can be irrigated across slope up to 5% by applying this contour furrows, and limited use of steep slopes in sandy soil and heavy black soils. That is usual because of more losses are possible there. Now, furrow irrigation system design based on the size and spacing. It was alignment because of slope, and now it is size and spacing. Deep furrows all type previous condition because of alignment. Either it's a straight furrow or it's a contoured furrow. Corrugated now. Corrugated means it is reducing in size after some time. So running water in a small furrows called corrugated means it is smaller. We are not taking a long or very long, but it's smaller as well. Crop rows are not necessarily related to irrigation furrows. Since it is independent condition. Reason being it is changing in its size. Used for irrigating close growing crops like small grains, maybe wheat, but usually wheat is not here, just like potato or any other vegetable crops, they are irrigated, maybe groundnut sometimes. It is more suitable in loamy soils and may be used in conjunction with border irrigation. Sometimes it's partially it is border irrigation, and then sometimes because of crop, because of soil, because of condition of the land surface, we are taking it as furrow irrigation there in the same field, and can be made with bamboo corrugation, means we are putting some wood or basically bamboo to make this a corrugated condition. Now adaptability, where it is adapted, which type of crop, which type of soil. So furrow irrigation, for row crops are crops, those are sensitive when water covers the crown of the stem. Crown means somewhere here, means this is on the surface. It should not be touched this stem of the crop. Just like maize crop, sorghum, sugarcane, cotton, tobacco, groundnut, vegetables like potato or any other, which doesn't require directly touching of water, but let us have a kind of channel here which is supplying water through this, and water will move towards the root from the bottom and from the sides to irrigate this particular crop. It is not suitable in sandy soils. Sandy soil because infiltration is very high and poor lateral distribution, means the moment it is sandy soil, you can see the characteristics of water movement in different soil. Suppose it is filled. If it is a sandy soil, water will go directly towards this direction. If it is a clay soil, it will go in this as well as in this as well. Reason being it's more time to move in all direction. But if it is sandy, immediately it will infiltrate to the parallel perpendicular bottom only. And that's why it is not suitable for sandy soils. Small plants require small furrows. Bigger plants certainly require bigger furrows to apply water, to get water in sufficient amount. So furrows of 7.5 centimeter to 12.5 centimeter are appropriate for basically vegetable crops, and we need to design size according to the requirement of the crop. What is the size? It's on the top and its depth, how much deep it should be, so that it can carry a certain amount of water in the field. What are advantages of furrow irrigation system? Water contacts only 1/2 to 1/5 of the field. This is the total field. We have furrows, so it is half of the field is only just figure if you are seeing here. One row, one furrow, one row, one furrow here. So it is 1/2 to 1/5 means area, just 20% area of the land surface, thus reducing various losses. Or it is supplied water in this particular area, half area to 1/5 area that is carrying water or supplied water. So losses will be reduced automatically. Earlier cultivation in case of heavy soils. Reason being, heavy soil are slowly taking water and slowly releasing water. So it is possible when it is furrow, half of the area is only applied with water. So early cultivation is possible in between the area or in this black soils or heavy soils. It can be used on a wide range of natural slopes without erosion by carrying the furrow across the sloping field. That will be a contour furrow condition rather than down the slope. So we can by using the contour lines. So furrows can be spaced to fit the planting or cultivating operations of standard machines. We can have one plant, two plant, and so on. Here maybe we have figure later on. What are disadvantages of furrow irrigation? Land must be graded such that water can travel the entire furrow without ponding water. Means there must not be a stoppage of water at a particular point, but everywhere it should be the same amount and same time condition. So opportunity time is same for every part of this land. Labor requirement, it requires labor to develop the furrows. So labor required is generally higher compared to basin or border irrigation. Previously we have learned. If we want to design, what we need to determine? So determining spacing of the furrow, at what spacing it should be in the field, what should be the shape, whether it should be B shape or it should be a U shape, and what should be the size in terms of depth and width of the furrow, what should be the stream size we are introducing, that is Q, and what should be the length of the furrow. If we these conditions design. So length certainly depends on soil, crop, etc. Let us discuss one by one spacing of the furrow. Spacing depends upon the row spacing of crop, like it is sugarcane, potato, maize. So we cannot have just same spacing for all the crops. Sugarcane may have wider spacing, potato may have smaller spacing, and so on. So we need to decide what spacing should be for this particular crop. Spacing lateral movement of soil moisture from this furrow lateral in such a way that it beds the ridge, means whatever ridge we have where we have plant here, by time irrigation is completed, means it is enriching the root zone of ridge that is side by or where the crop is grown. Sandy soil should have closer spacing than the clay. Simple reason, it has high infiltration rate. So if it is apart or longer spacing is there, area in between two furrow will not get sufficient amount of water. So sandy soils will have or certainly have closer spacing with respect to clay soils. What about the shape, spacing, then shape and size of furrow? The shape of the furrow, it depends upon the soil stability. If it is sandy, certainly we need to have V shape, and if it is black soil, then we can have perpendicular sides. So U shape we can have. So slope of the land, not only the soil, but slope of the land and type of the implements used for making furrows. So A type, bullock drawn or machine drawn, or it is a disc furrow opener, something we need to find out what facility it is available to develop the furrow condition in the field. For steeper slope greater than 0.5%, broad base furrows are recommended. Broad base means it is having a kind of broad base, wider base furrow because of high velocity and less depth of water. For shallower slope, steep sides means perpendicular, we can have furrows are useful. Reason being they are not eroding the soil. Too high ridges are advantageous in areas where excess rain means if it is excess rainfall, so we can have bigger or wider ridge we can have to dispose of any excess rainwater that is discharged or runoff safely, but requires a large stream size to irrigate the top parts of the ridges. So it is means if it is a bigger size, so we need to have bigger stream to apply water so that root zone is replenished with water. So we need to take care about such condition. Height and slopes determine the capacity of furrow means if it is height and slope that determines the capacity of flow, just like we have learned in open channel design. Now this is the simple idea how this furrows are working. So shape of furrow and opportunity, shape of furrow and position of the planting, just like here. Single bed furrow, double bed means we have multiple trees or multiple plants. If it is saline water, we can have not on the top because any salt is accumulated at the top, automatically it evaporates water, so salt are accumulated at the top of this ridge. So plants are planted a little bit down than the top ridge. Different water quality. Initially, if you recall, we discussed about the water quality. So it is towards the side of this furrow we are planting, or it is another side. We have furrow and both sides we are planting here. So these are different arrangements of planting or cropping in furrow irrigation system depending on soil property, water property because of salt accumulation, and because of water quality itself, which is supplying water for the survival of the plants. So this is the simple idea how we can design the furrow irrigation system. Stream size should be non-erosive in furrows and within the capacity of the furrow means how much amount it can carry, and velocity should not otherwise it will be erosion problem in this channel or furrow channel section. General value of stream size, it is simply 45 by S, where S is the slope. If it is 1%, can go 45 centimeter per second and something like that. So this is designing of furrow condition for irrigation purpose. And this is general guideline to minimize the land grading operations used should be adapted to natural topography. Slope of the furrow should be do not cause any erosion problem. And That's why it is maximum allowable slope we have for different soils. If it is sandy soil, we can have lesser slope. If it is clay, we can have some slope because we can increase the slope. When slope exceeds the safe limit, furrows across the slope on the contours, it creates a problem of erosion and less availability of water. So this is idea of furrow development. Furrow length that is influenced by the slope, rate of advance and depth of application. We need to design what should be the furrow length. It should not be like means maximum. We need to take care about the soil property, rate of flow condition means how much rate it is available we have, and what is the advance and depth of the stream size, slope and furrow length should be adjusted in such a way that the deep percolation losses are minimized. Means all these conditions in such a way that loss of water below the root zone depth, that is deep percolation, is not there. Otherwise, efficiency of water application will reduce. And what, as you asked earlier, what is the most important? It's uniformity. Everywhere it should be, and that's why we have faster movement of the stream. But efficiency is at the same time important. Any loss of soil, that is erosion. We take care about all these conditions to find out what should be the size of any of the irrigation method, what size of stream it should be used, and for how long in terms of its design, length of furrow, border, or size of basin. So these are some guidelines, typical furrow length for various soils, like it's a coarse, medium, fine. Application depth, suppose we need to have 50 millimeter application or 150 millimeter, three application depths, it is discussed here. If slope of the furrow is 0.25, discharge characteristics is, for an example, 180 liters per second. So furrow length in this range. If it is fine sand, fine soil condition like clay, for different application rate, we can have slope characteristics just like 0.25. We can have discharge 180 liter per minute, and length can go up to 300 meter. Our maximum it is 530 meter. That is for application depth of 150 millimeter. Minimum 25% from the source water discharge we have available 180 liter per minute. So we can go up to 530 of the furrow. In that way, we can take this kind of as guideline to decide for a specific case or a specific area requirement of irrigation by this specific case of furrow irrigation. Response of the water should be such that minimum percolation loss are caused at the head, because head it is from where water is diverted to this furrow or basin or border. So minimum loss of water because of percolation, because this is the area which receives maximum amount of water, means from the beginning, and when it is cut back or stop the supply, even that point it has sufficient of water. So loss of water is minimum from this point. One particular Cradle in 1956 suggested that the value of T by 4, that is time requirement to infiltrate the required depth of water, that should be the time of advance. Usually we should take T by 4. So time required to infiltrate the required depth of water. We know the infiltration rate. We know how much millimeter per unit time. So total time to infiltrate D depth of water, we can find out that is T. By basically the advanced time we should have in the field. These are the design guidelines. So now it is a problem to understand better this furrow irrigation system. Can you do one more? Furrow of 90-meter length or long is spaced 75 centimeter apart. This is furrow, that is 90 meter, and two furrow means center of this furrow to center of this furrow. This difference is centimeter. This is 90 meter here. Are irrigated, apart are irrigated by an initial furrow, means this is the area which is irrigated by initial furrow stream of Q is equal to 2 liters per second. The initial furrow stream reached the lower end of the field in 50 minutes. It reached here in 50 minutes. So T is equal to 50 minutes. The size of stream was then reduced, means now it is Q dash, that is 0.5 liters per second. The cutback stream, this is called the cutback stream, continued for 1 hour. So T dash is equal to 60 minutes. So what is the average depth of irrigation? Assuming there is no loss, our efficiency is 100%. Can you try? Anybody still here in the class?
Yes, sir.
Okay.
Yes, sir.
So can you try this?
Yes, sir. Will try.
Okay. So try this and bring the answer. Write down this now. I am giving you just 2 more minutes to write down the problem, solve it, and bring me the answer in next class. And did you discuss among yourself when I can get 2 hours time to finish the remaining portion of irrigation method, that is drip and sprinkler? When can you give me 2 hours time? Friday, Saturday, Sunday? Note down the problem. I will ask each and everyone individually now. Attendance downloaded, 36 students present. Here is the problem. The next I need to know from you, which day you are giving me 2 hours time to finish drip and sprinkler irrigation method. Nobody is speaking. In between you can
Sir,
speak while
we will
writing.
let you know by
Yeah.
the end of the today, for sure.
Monday you told me that we will let you know, sir, on Wednesday. And today is Wednesday, tomorrow is the Thursday, that is the last class. Then after I need. And if you want to give me tomorrow as well, you just suggest me by an email. Okay? Certainly tomorrow I need to know. I get 2 hours because earlier I gave you more time initially, and that's why it is 2 hours shortage. Finish the work. So give me tomorrow your decision, right? When I can
Yes,
get 2
yes.
hours to finish remain irrigation methods. So have you noted down this problem?
Yes, sir.
Okay. So bring the answer to me tomorrow. This is simple arrangement of ideas what you have learned. I want to know what will be the average depth of irrigation there. Okay. So here we learned the surface irrigation method. Uncontrolled flooding is usual, no problem because water limitation is not there. So you can flood the area. Remain 3 methods are border, basin, and furrow method. You learn about advantages, disadvantages, different conditions because of soil characteristics, because of slope condition, because of crop requirements. So we can find out the optimum design so that uniformity of the irrigation is maximum and efficiency of water application as well is maximum. So this is our target in designing the irrigation method. And if you have any query, you please bring to me next class. Okay? Is it
Okay,
fine?
sir.
Okay. Then have a break, go for next class, and we will meet tomorrow again at 10 o'clock. Okay? See you then.
Thank you, sir.
Okay, welcome.
Thank you.